Okay, continuing on. We have this thing called the DHCP state machine. So this is basically going to be what DHCP uses as kind of a decision-making process. And it kind of determines what the type of messages that need to be sent are. So basically it's going to be kind of like a dichotomous key. It's going to be kind of a roadmap to help the decision-making process overall for the server or the client. So this is going to be the state machine. So you can see towards the top you have the discover. So you have the init or the initial state, and then you have this send discover message, and then it ends up in a selecting state. And so it's going to be collecting offers at that point, and it's still in that selecting state. Then it's going to select the server and send the request. You're going to be sending that DHCP request, which is going to put you into a requesting state. And then you go into the receipt of the ACK or the DHCP ACK or the accept, and then it's going to be in a bound state. And that's where you're going to have that T1, T2 aspect to it. Now, if we get up to the requesting state again, and you go and you say it's going to be a NAC or we're going to do a DHCP decline, we go from requesting back to that initial state. So previously, when I had said we go through the process again, it's because we go into that initial state again, and we go through that process where we go discover, offer, request, acceptance through the process. So we basically go through this kind of loop until we get that ACK message. And so then towards the bottom, when you're in the bound state, you hit T1 and you get to a renewing state. Now, if you go to renewing, you make the request, and then you receive an ACK, then you go right back into the bound state. And you go through that loop over and over and over again until you either A, hit T2 and you go into a rebinding, or you give up or B, you give up your IP address to an IP release, or there is some other circumstance in which you need to basically go back into your initial state or into the rebinding state. So if we get into the renewing state and we can't renew, then T2 happens and we get into the rebinding state. And then the rebinding state again, if we get that ACK from a DHCP server, then we're good to go. Or if the lease expires or we receive a NAC, then we're going to move right back into that initial state again. So it's this kind of it's a big diagram of just loops. So we go the initial loop through the bound, and then we go renewing, and then rebinding, and it's just all the different states that we can be in while we are dealing with DHCP. So then now let's dive in and talk about DHCP relays. So DHCP clients are going to rely heavily on broadcast messaging to obtain IP address information. So again, right when you come on the network, you start broadcasting out for a DHCP service. So, again, we have routers, and routers are going to drop those broadcast messages. So the implications for DHCP is really if we do not have what we're going to call a DHCP relay, something that allows DHCP to be connected to outside of our local area network, then we would need one DHCP server per network. Now, if that's a home network, not a big deal, right? Because you probably only have one network or a couple of networks. And even in that case, it would be kind of a pain to have separate DHCP servers per network. But if we get, and especially if we get into a large network, for instance, picture 100,000 clients over multiple locations, or even just multiple departments and different VLANs on the same LAN. When you get into that type of situation, now we could have 30, 40, 50 plus DHCP servers, and then we'd have to manage all of them. There is no central configuration for any of those, or a way to kind of manage all the DHCP servers from a single pane of glass, or at least easily. So we implement this idea of a DHCP relay. And so the DHCP relay is going to help us get around this constraint of routers dropping broadcast messages. So we have the DHCP relay, and it's going to be placed at the edge of our network. Now, typically, it's going to be either our core switch or a router, whatever is going to be dropping those broadcast messages, and it's going to it's going to facilitate the communication process for DHCP. So the broadcasted message is going to be sent out, and then the DHCP relay is going to take that broadcast message, and then it's going to change it into a unicast message, and it's going to send to the remote DHCP server for processing. And so it's just this facilitator. It's going to just basically hand back and forth messages between the client and the server that is on a remote network. So ultimately, we go into this process a little bit more in depth, but where we got into the different fields in Wireshark, for instance, if we go back to Wireshark, we have the relay agent IP address. So if we actually put if we're using a if we're using a relay agent, then we'll put that IP address here so that when the DHCP server sends it back to the relay knows exactly how to send it back to the client. So it's, again, that facilitation process. And DHCP v6. So I'm just going to touch on this briefly, but DHCP v6 is going to. There's two ways you can set it up. You can set it up to be a stateful version like we saw in IPv4. However, it's not very common, and the biggest reason that is because IPv6 can configure a lot of its own information. For instance, IPv6 can come up with its own IP address through stateless auto configuration, and then it can also come up with its own router or default gateway through router solicitations from IPv6, and it can come up with a lot of other information just all by itself. So there's not really a real good reason to have a full stateful version of DHCP v6. So typically, if there is going to be DHCP v6, it's going to operate in the stateless version, and so the stateless version basically is going to serve out options. So the options that we talked about for where to go for configurations, some of the different pieces of information that it can't automatically get from IPv6. That's what the DHCP v6 is going to be able to dish out. And so you can always rely on a consistent configuration, but ultimately still not going to be a full-blown implementation of stateful DHCP like we saw with IPv4. So I would encourage you to go take a look at the stateless DHCP v6 video that I've attached here. It gives a little bit deeper of an overview, but ultimately I just wanted to touch on it to make sure that DHCP v6 was talked about a little bit. So I mentioned stateless address auto configuration just a second ago, and so we took a look at IPv6 and stateless address auto configuration. Now, again, if you recall, we can basically take this unique value, which is almost always the MAC address, and we can flip a bit and make that unique and then turn that into an IPv6 address for us to use. And we know that there's a high probability that that's going to be unique to us. So again, I would encourage you to take a look at the link there for more information on Slack or stateless address auto configuration. So we have DHCP snooping. So a lot of times we have network devices and we inspect the contents of DHCP and we ensure that they're coming from an approved ACL, also called an ACL or an access control list. So this is going to help us prevent rogue DHCP servers from operating on the network. So what is a rogue DHCP server? Well, if you think about DHCP servers living inside of your what a lot of people call your wireless router. So when we think about this type of device, we have a box. And inside that box is a switch, is a router, is a wireless access point, and is a firewall. And then it's also a DHCP server, it's also a DNS server, it could be an FTP server, it could be all of these different things, it could be anything that it wants to be almost. At least that's how it seems. But it can be so many different things. And so, like I said, one of the things that it can be is a DHCP server. Now, what if I take one of these so-called wireless routers and I plug that in to my enterprise network? What's going to happen? Well, if it's on the same network segment, or other people are connecting to it because it's maybe open Wi-Fi, there's a potential that it's going to start serving up DHCP leases to these clients. Now, why is this a big deal? Well, if we think about what we could do with something like this, if we're not providing some sort of access control list, is, we could potentially have somebody who's malicious and comes onto our network with a DHCP type device and starts handing out information that could potentially help them with man in the middle. It could help them serve up information that's going to compromise their device, to send them to rogue DNS servers, tons of different attacks that you could potentially do with a rogue DHCP server. But ultimately, it's an annoyance. It's a higher risk. And it's doing stuff on your network. It's providing IP addresses and option information that it shouldn't be. So with DHCP snooping, it allows us as administrators to limit kind of what hosts can receive IP addresses on the network. And additionally, we can also authorize which DHCP servers can provide addresses in our environment. For instance, from a Windows DHCP server point of view, we can say which DHCP servers are allowed to provide addresses, and if we get addresses outside of those, don't honor them. So that's another step that we can take to reduce risk with rogue DHCP servers. But ultimately, with DHCP snooping, it usually uses a MAC address, which is pretty trivial to work around, so it's not always the most effective method of stopping these types of attacks on the network. And truly, with some of these different types of scenarios, it's hard to find a rogue DHCP server on the network. Just because you have to physically kind of figure out where it is, and a lot of times it's somebody who doesn't know that there's a problem with it. So just something to keep in mind. But ultimately, what I want you to recall here is just that DHCP snooping can kind of look at the contents of DHCP to make sure that they're coming from an approved ACL. So it's not somebody just joining your network, trying to get onto the network with a valid configuration. Okay, so that wraps up DHCP. So now I'd like to move on to DNS. So domain name system, or DNS, is probably what makes the world go round. If you look at certain things like the sysadmin subreddit on Reddit, people would say that all problems resolved to DNS on a network, which is kind of a funny, sentiment, but the point that it makes is DNS is so important and is so integrated into our current day or present day networks that if there's a problem with DNS, everything is broken. You have problems. Another example would be Dyn DNS. Back in, I believe that was 2006, Dyn DNS was taken offline, not 2006, 2016, and Dyn DNS was taken offline for a period of time, and there was good portions of the internet that were broken. You couldn't get to them because DNS doesn't work. DNS is so ingrained in what we do that it's so important that it can cause major problems. But it also really helps us out with a lot of stuff. So let's dive into DNS. So the domain name system. So, up until this point, we've been talking about network communication using IP addresses. But everybody knows that we don't browse to, 216.something.something.something to get to Google. We go to www.google.com. And so we as humans are great at remembering names. We're great at remembering how to browse to these different names. But we're not really great at remembering numbers. Machines, on the other hand, or computers and servers, are all about numbers. I mean, they operate basically in binary. When you think about getting to the CPU level or to the network transfer level, we're dealing with bits and bytes there. So ones and zeros when we're talking about bits. But basically, this means that we need to find a way to seamlessly transition between host names and IP addresses. So this is where we queue DNS. So DNS is, like I said before, it's so important to us. It's important to networking. It's important to the internet. Without DNS, we really wouldn't have a very easy go. For instance, I think that almost one of the best examples for this would be if you've ever tried to surf on Tor. So Tor, is a very decentralized form of, obfuscating the internet and having specific hidden services, and so there isn't really a DNS. There's not really a DNS server or service that's readily available for everything that's on Tor, for a good reason. But also, that means that you basically have to, copy paste these weird addresses and things of that nature. It would be very similar to that if we were operating the internet without DNS. So a side note, I don't necessarily advocate for anybody who's not experienced with security and Tor in general to go and use Tor. There's a lot of bad stuff out there. If you don't, I would highly recommend not going on Tor unless you have a very good reason from a security research or a different security perspective. If you have questions on that, please talk to me, and we can talk about the safest way to do that. But it was just an example to kind of illustrate how important DNS is to us as humans navigating the internet. So DNS overall is hierarchical in nature. So we have domains, we have subdomains, we have hosts, we have top-level domains, we have a root. So we have all of these different levels, and we'll get into how they relate to each other. But we use this client, and we use this client-server architecture. So where we make requests saying, "Hey, I need to know the IP address for this particular host on this domain," and then the server goes and responds back and says, "Here's your mapping." So then we get this mapping, and it's mapping a host name to an IP address. And so IP address in this case doesn't necessarily mean only IPv4. In a lot of past lectures we've talked about specifically IPv4. Well, with DNS, it can map to IPv4 or IPv6. As far as ports, so DNS will operate on both TCP and UDP port 53. So we'll get into the reasons of why it would operate on TCP versus UDP and vice versa, but it does operate on both. And then, basically at its core, DNS is going to be a series of records. We have different mappings from host to IP address. We have mail exchanger records that talk about email addresses. We have different text records that could be used for kind of free-form records or SPF records for email security. We have a whole bunch of these different kinds of records that help us to map or to resolve these names to IP addresses. So this is the hierarchy of how DNS kind of works. So at the top, you see this period, and that's the root. Okay, so that denotes root. Then we have top-level domains kind of in the green box, and then second-level domains, subdomains, and hosts. So a lot of times, for instance, if we go to www.google.com, we would say that we'd have the root, which would be the period kind of at the end, and we don't put that in our URLs and our fully qualified domain names, although you technically, I believe you can. It's just not necessary. It's kind of a piece of information that is assumed. But we have the top-level domain. In this case, the top-level domain is going to be com, it's going to be mil, it's going to be edu, it's going to be, the amount of top-level domains at this point has kind of exploded. But top-level domains are going to be those kind of well-known domains that we're all very familiar with. And then second-level domains is going to be like Google, it's going to be Metrostate, it's going to be, Cisco, it's going to be a whole bunch of different second-level domains. And then you have subdomains and hosts. So you could probably have said, subdomains is level and hosts is level. But realistically, when we're navigating the internet, it's kind of not one way or the other whether there's specific subdomains or just a host there. So in the case of www.google.com, there is no subdomain below the second level domain. It's just going to be www, and that's going to be the name of the host. Whereas if we could have another subdomain, say it was www.mail.google.com. Now, that's not a valid domain or a fully qualified domain name, I don't believe, but that's just an example of kind of how that could potentially look. At the example there, you kind of see how the different layers are written out, where you have host, subdomain, second level domain, top level domain, that's going to be your fully qualified domain name. That's exactly how you would map out the host name or the DNS aspects of where you're trying to go. So now that we have this kind of idea of a domain, then we need to have things that are associated with our domain, such as name servers and zones. So name servers, we want to have a minimum of 2 DNS servers that are authoritative for keeping information regarding your namespace or your domain space. So we have a primary server and we have a secondary server at minimum. Typically for larger organizations, things like Google, you will see like 4 name servers that, and all of those are going to be authoritative for that particular zone. And so we have the primary servers and the secondary servers, and the information is going to be transferred between them from the primary to the secondary in what we call a zone transfer. So basically it's going to help us keep information, it's going to help it be consistent, it's going to keep it updated between the primary and secondary servers. So then we have namespaces that are going to be split up into DNS zones. And so basically zones are going to be little pieces that are carved up. For instance, we have the com namespace, for .com, the com top level domain. And so that is this huge area. Okay, it's this huge namespace. And so we carved that down a little bit into Google. And then that's a specific piece of that top level domain. So that's a part of a zone. And then even further below that, we could carve that up even more into different subdomains that are in that zone. And so we create even further divided subzones. And so we have all these different zones. And then for something like a second level domain, that's where we're typically going to identify what our name servers are. And that's where all of our information for our domain is going to be housed. So in this zone, we are going to have a whole bunch of records. And the records are going to be for mapping these IP or host name to IP address. And it could be potentially a nickname or an alias for a host name. So it's going to be all these different kind of records that we'll talk about here shortly that are going to be included in the DNS zone. And so all domains are technically included in a zone. We have a root zone, and that's going to be, like I said before, that top level domain, com, gov, edu, what have you. And again, those get chopped up into smaller pieces. So what we do in a lot of cases is we will say that particular DNS domains are delegated to allow for control to the domain. So for a top-level domain, if we have a portion of that namespace and we don't specifically say that you own this or you can administer it, then technically you really can't. So all of this stuff, the DNS administration process is really very delegate heavy, and so we have to delegate the ability to do those things. So again, think larger pieces up top, and they get subdivided down into smaller zones. Another concept that's very important for DNS is DNS caching. So similar to when we talked about ARP caching, we talked about MAC address tables, and we have these different devices that are checking their respective caches for specific types of information. It is the exact same thing. We have a DNS server or we have a DNS client that has a cache of their own. And so this is meant to improve efficiency and effectiveness of DNS. So DNS is happening all the time. We have tons and tons of different DNS requests that are happening all at the same time. And so to try to reduce the traffic associated with DNS, we will cache our DNS queries for periods of time. And that's going to be part of the TTL. And so then that allows us to just look in our cache and obtain that DNS mapping and then go and make the communication based on that IP address. And so again, we have this TTL value, and basically what we will do is we will let this record live in our cache until that TTL expires. So what are some pros and cons with TTL values? Well, from a low TTL perspective, that would mean that we could have frequent changes to our DNS records, and because that TTL will expire, we will go and re-query for this information on a more frequent basis. So we can make frequent changes. But on the negative side of that, that means we have more network traffic. But let's say we do a long TTL, so we make it be several days or longer than that. If we make a change, then it's going to be a much longer period before our DNS information is going to be updated for clients. So for different scenarios where we have more volatile infrastructure, we have changes that are made quite frequently, we might want to choose a TTL value that is going to be lower than perhaps an infrastructure that changes very, very rarely. So just something to consider with that. So DNS caching is going to apply to both successful and successful resolutions. So obviously, if we resolve a particular hostname to an IP address and we can validate that that's good, then we cache that, and that's great. But we can also do an unsuccessful resolution and cache that as well, so that we don't try to make another unsuccessful resolution in the future. So then we have the DNS protocol. So there's two main parts. There is the query/response, which is going to be kind of the most common usage. Hey, I need the IP address for www.google.com. This is how we are resolving our host names to IP addresses, and we go through this process where we iterate through the infrastructure to find the host name to IP address mapping. But then there's also the database record sharing kind of zone transfers part. So we have DNS servers sharing information with other DNS servers. So this is where we get into kind of the notification of secondary zones, that changes have been made with the DNS notify, and then we also have dynamic zone updates where it just kind of happens on the fly. So root DNS servers and global top-level domain DNS servers. So root DNS servers, these are going to be the ones that are at that period at the top. They're at the very root. They are going to house all of the information for top-level domains in the world. So technically, there's only 13 of them, and they're labeled A through M. So DNS server A through DNS server M. And all of them have IPv6 addresses. So the textbook is a little bit outdated on this. I believe it said there was like 9 or something like that at the time the book was published. But all of them nowadays have IPv6 addresses. And then you have also generic top-level domain DNS servers, and they follow a very similar structure. So we have com, net, org, gov, all of these top-level domains. And there are 13 of those as well, and so there's going to be, generic top-level domain server A through M. But basically, so it says there's 13 of them. However, they are going to be in kind of clusters, and they're going to be placed at various places in the world. So, for instance, root server A might have a location in Minnesota, might have one in California, might have one in Great Britain, might have one in China. And we'll see the graphic here shortly. But basically, they're spread out in clusters, and there's definitely a good reason for that. But it's going to use an Anycast mechanism to contact the root server that's going to be closest to you. And we'll talk about that here in just a second. But basically, they're going to share IP addresses. They're going to be distributed groups of servers. And basically, again, we're using Anycast to get to that closest DNS server. So, for an example, all M DNS servers are going to share the same IP address. All A servers are going to share the same address, and so on. All the information across all of those servers, all the A's will have all the same information. All the M's will have all same information. All the D's are going to have the same information. And so, why do we do this? Why do we have this distributed architecture? Well, for one, we have these DNS servers, or this DNS type of service is so important to us being able to communicate on the internet or on our networks. So we need to have redundancy, we need to have resiliency. But also, think about this redundancy and resiliency from a security perspective. If we took out DNS, as we saw with the Dying DNS attack in 2016, that had a significant impact on being able to visit certain e-commerce sites and services, like I believe Netflix was one of them, from being able to legitimately use that service. So we spread these things out for performance, we spread it out for resiliency, we spread it out for reliability. So this is all the root servers, A through M. You can see the IP address. You can see that all of them now have IPv6 addresses. Then you have the autonomous system number. You have an old name, who operates them. So you can see VeriSign. You can see Cogent, University of Maryland, Internet Systems Consortium, Defense. U.S. Army Research Lab, again, VeriSign, ICANN. So a whole lot of these different, operators and organizations that are well known that are running these root servers. And so, again, for almost all of them, you have Anycast that we're using, so we get the closest. And obviously, the one that we're not necessarily using Anycast for is for root server H, which belongs to the United States Army. And then you see different software there. So Bind is a very popular one, so is NSD. So you have different kind of DNS servers there, or DNS service or server types, excuse me. And those are going to be there as well. So this is the root servers that we use. And so this is kind of how the root servers are distributed throughout the world. So you have let's say, take a look at J. So we have J that's going to be in Seattle. It looks like Seattle at least. So in Washington, we have J's that are in Alaska. We have J's that are in Europe. So we have the United Kingdom. We have up towards, the Scandinavian countries. We have them closer down towards Greece, and so you can see how they're all spread out amongst the world. Including the lone DNS server in the middle of Russia. So, there's a whole lot of spread out DNS infrastructure throughout the world. So, now I want to get into kind of how DNS is starting to work. So we have two types of kind of main queries or roles in DNS. So we have recursive and we have iterative. So recursive, when we have a recursive query or recursive DNS server, basically what we're saying is we're going to have another device conduct all of the DNS request process on our behalf. And then they're going to go out, they're going to go find that information, and they're going to come back and provide it to us. And so it's going to reach out to other DNS servers and resolve that host name to an IP address. The client, clients, on computers that are workstations that people are using, typically are going to utilize another DNS server and have that DNS server be a recursive DNS server on their behalf. So you don't have a client that's reaching out to do the entire process. And then you have iterative. So the recursive DNS server is going to iterate through the different levels of DNS servers, and it's going to get more information on how to find that host or that domain and map that host name to an IP address. And so each DNS server contacted during this process is only going to have basically more information on where to go next. So for instance, COM is only going to have information on how to get to Google. Google's DNS server is not necessarily how to get to www.google.com. So it kind of gets through this process, and we'll see that here in just a moment. So this is going to be, generally speaking, how we go through the DNS request process. So we have a client there that's at number one, and we want to say, what is www.google.com? And number two is going to be our DNS server that is going to be our recursive DNS server, and it's going to perform the iterative queries to the other servers. So in this case, we have this DNS server, and the DNS server at number two is going to say, I'm going to check my cache and see if I've already done this. And it's going to check his cache and say, do I have an IP address for www.google.com? And in this case, no, we don't. Okay, so what we're going to do now is we're going to say, hey, root server, and this is going to be part of our root hints on our operating system, or in the DNS server, it's going to know where the root servers are. It's going to say, hey, root server, do you know what the IP address is for www.google.com? And the root server is going to say, I don't. However, I know that com, the top level domain com, that DNS server is located at 1.1.1.1. Now, this is a fake IP address for this example. That's not going to be necessarily the IP address that it would use for com, but it's an example. And so the recursive DNS server is going to say, thank you, I appreciate that. Now, how about I go talk to com, and it's going to say, hey, com, the DNS server for com, what is www.google.com? And the top level domain server at com is going to say, I don't know what the record is for www.google.com. However, I do know that the DNS server for google.com is at 2.2.2.2. And so the DNS server number 2 is going to say, okay, great. Now, hey, DNS server at google.com, what is the host name, or what is the IP address for www.google.com? And that name server is going to say, oh, I do have that record, and www.google.com is going to be at 3.3.3.3. And now at this point, the DNS server at number 2 is going to say, great, thank you, and it's going to then cache www.google.com at 3.3.3.3, and then it's going to pass that answer back to the client and say, hey, client, I went and did your bidding. I iterated through all those DNS servers, and I found out that www.google.com is at 3.3.3.3. And now that client can go and make its HTTP requests to 3.3.3.3, even though we are typing in www.google.com. So for more information on kind of how that DNS request process works, I would encourage you to take a look at the link here. It'll go into a little bit more depth on how the DNS request process works. But if you kind of understand the process that I just laid out there, you're going to be fine. One other note that I do want to add in is that number 1, the client will also add in www.google.com at 3.3.3.3 to its DNS cache. So it doesn't actually have to ask for it next time. It'll just store that in its cache. Now again, remember that when we're storing the cache, there's going to be a specific TTL that is going to be associated with these DNS requests, and it is going to be it'll stay stored in that cache for as long as that TTL value is valid.